Well, in this lesson, we're going to talk about solving complex logarithm equations. Complex logarithm equations. Previously, we talked about how to solving logarithm equations. We went through many examples, and at the time, we reviewed the relationship between logarithm functions and exponential functions. We just solved some, in the last lesson, we talked about solving exponential equations, right? You can see for solving exponential equations, we don't have any issues with domain, but we have to check the range in order for the solutions to make sense. And we reviewed the graph, and we have solved various exponential and the logarithm equations. And these exponential and logarithm equations, they all have, it's complexities, and we have done the simple ones. And this is time we're gonna work on the more complex ones. Okay. So you can see these are the examples we've done, right? For a simple logarithm equation, we know the output and what we can do, and the variety of methods we talk about, okay? So without further ado, we're gonna continue to solve complex logarithm equations, okay? Now, before we solve the complex equations, there are a couple of things we like to review. One of them has been the product rule, quotient rule, and the power rule of logarithm. And these are the rules that we have covered before, which is a logarithm base B, right? If we have a sum like this with the same base, and A and B are in the domain of logarithm, and that equals to a product, A times B. If we have logarithm base B, capital A, subtracting log base B of capital B, and that going to equals to log base B of a quotient. And the third one is that if we have a constant, multiply a log base of capital A, and that's going to be equals to log base of the same base, capital A to the power of C. Okay, so these three properties are going to be useful in solving complex logarithm equations. So let's see, what are the complex logarithm equations? And I take questions from the homework. Okay, I take questions from homework. The first one, okay, example number 1. Okay, and here we have a logarithm base 5 of x, 5 in the wrong place, plus log base 5 of x plus 1. On the other side, it equals to log base 5 of 20. Okay, so this is a logarithm equation. Of course, we can see it from different perspectives. We can see this as this is a function, and that's the output given. Solving for x, of course, right? So this is a if statement. This is an if statement. Okay, this is an if statement. To solve it, and we're gonna, think of how to do it, right? So this means that if this is true, right? And we like to make a single logarithm on one side, or you can make a one single logarithm altogether, right? Anyway, it's fine. Okay, this is what I meant. One way to do it is that you make a single logarithm on one side as is, right? Using the product rule, we have a common base 5. We have a common base 5, right? So we can just write it as log base 5 x times x plus 1 equals to the right-hand side. Okay, and then because log base 5 is a one-to-one function, right? So let me put this as think out aloud. Okay, we're still just working out this on the scratch paper. Okay, on the scratch paper. Okay, so this is our scratch paper, right? So we'll try to figure out. Then the fact that log base 5 of, I would say omega, right? This is a one-to-one function. It's a one-to-one function, right? And we have reviewed those concepts, right? Log base 2x, log base 3, log base 3x, natural log x, log base 10x, log base 5x. In general, this is a one-to-one function. As a result, right, the output are the same, and therefore the input are the same. Okay, so this is a one-to-one function, right? Well, in fact, it's an increasing function. So when the output are the same and their input are the same, so the next step will be x times x plus 1 equals to 20. So we end up with solving a quadratic equation, right? So this is one aspect to it. The other aspect to it about solving this equation is not only algebraic, you use these products, is that we have to consider something called domain. Okay, I put an exclamation mark here. Domain. So before we do this, before we work out these steps, we need to guarantee that x are going to be in the domain. So in this case, the domain consideration has to be for all of the functions and expressions involved. Okay, so in our domain consideration, we not only need to guarantee that this expression is meaningful, we also need to guarantee this other expression is meaningful. And this one, of course, is meaningful. 20 is larger than 0, right? The fundamental reason is here because you see the domain for logarithm is that whatever that the function applied to has to be positive, whether it's the x or it's omega. Whatever the logarithm that applies to the input, that input has to be positive. The output are all real numbers. That's not a problem. So whatever the rule of the function applies to, that has to be positive for all of the logarithm functions. For this reason, when we need to first determine the domain. As you see that in the homework session, we ask you to do what? We ask you to determine the domain and then solve for x. Okay, so that's the title. That's the title. So for this reason, we're going to determine the domain. Now, for this function, we have to guarantee that x is larger than 0. Okay, and for the other function, which is x has x plus 1, so we have to guarantee that x plus 1 must be greater than 0. So we have two requirements, and these two requirements has to be connected by and. That means that both conditions must be satisfied. Both conditions must be combined. So as a result, right, x larger than 0 is already simple enough. Then we just have to, solve for x plus 1 is larger than 0. So as a result, x is larger than -1. So x is larger than 0 and x is larger than -1. And what's the consequence of combining these two? What's the consequence of combining these two? To figure out this combination, we just have to look at the number line, right? On the number line. We have 0 on the number line, right? And we have -1 on the number line. Okay, so let's put this as a -1 and over here as 0, right? And this is the number line. And we want both are satisfied. So larger than 0. So here are larger than 0, right? And over here, these are larger than -1. Okay, the place that we marked twice satisfy both conditions. So the combination of these two requirements will result in x is greater than 0. Okay, so the final domain is, and we will need this, we need to come back to look at this condition. Why? Because we will need the solution has to satisfy this condition. Okay, so let me give it a try to see if I can graph this better. Okay, I know we can. Okay, just give me a little time. Okay, so I'm going to set up the rectangular system. So we want to make this picture more durable, right? We don't have to move it all the time. So I'm going to set up like that, okay? We want it to be larger than 0. Larger than 0, we're going to mark, right? I'm going to add a point that's 0, 0, because 0 is not included. So it's going to be a circle. Okay, and to the right of 0, and to the right of 0. Okay, so that's going to be 0, 0, right? So that's going to be the domain that show up on the number line. And I'm going to remove these and make this more like a number line. Okay, so let's see. Let me make one more little adjustment. One more little adjustment. So this should do it. There, that's what I want to show you. Okay, so just the number line. So this number line shows the domain. Larger than -1, larger than -1. So I can actually make one more adjustment. Okay, larger than -1. So let me just write it from -2 here, right? From -1, that's just not going to make it, because larger than -1 is not enough. It has to be larger than 0, right? Both conditions must be satisfied. So this domain requirement must be satisfied. Okay, so this is the first part, solving this kind of equation, okay? And then everything we do is in the domain. Satisfy the domain requirement, satisfy the domain requirement, okay? So now I think we can just start showing the work. Okay, we start to show work. All right, and we're gonna finish, right? So we're gonna show work. Show work, we start with determining the domain. So we're gonna have this part. We're gonna have this part, okay? And then we're going to work out these pieces. right? So everything works, everything is done in domain, okay? You can quote this reason, right? You can quote this reason, and you probably like to quote the reason on the side. Okay. Wait, I think I did that. Wow. Okay, I think we just don't have to go there. It's for one-to-one function, or you can say, just quoting the reason. Okay, I deleted and all right, so we can say one-to-one function, same output lead to same input, right? So one-to-one function will be a good reason. So next, we ended up solving this quadratic equation. We ended up solving this quadratic equation. So we're gonna have x squared, okay, x squared plus x equals to 20, okay? And make 0, so x squared plus x minus 20 equals to 0. Factor, right, factor. So we get a x plus, well, x plus 5 times x minus 4 equals to 0, right? And then principle number 5, x plus 5 equals to 0, or x minus 4 equals to 0. So in the end, we get x equals to 5, or x equals to 4. Or negative 5, sorry. X equals to negative 5. And this is the time we're going to have to check if these two numbers, if every one of them is in the domain, right? If each one of them in the domain, that's the first check. So we're going to do the domain check. Okay. Domain check tell us that x equals to negative 5. Okay, you can say negative 5 is not in the domain. Thus, it is not a solution. X equals to 4 is in the domain. But just because it's in the domain, it doesn't mean it is going to make the equation true, right? So we're going to check for x equals to 4. So x equals to 4 in the domain, right? But that's not enough. In the domain is not enough. We have to go back to the original equation. Okay, we have to go back to the original equation, okay, to make sure the left is equals to the right. The left equals to right. Okay. So now x equals to 4 and substitute x by 4. On the left-hand side, it equals to log base 5 of 4 plus log base 5 of 5, right? And that using product rule, we have log base 5 of 20, right? 4 times 5 is 20. So left equals to right. So we can say equals to right, left equals to right at this point, right? There's nothing, we don't need to do anything on the right. So we can actually just remove this. And now is the time to make the claim. Therefore, right? Therefore, then you can say x equals to 4 is a solution to the equation. Which equation? Right here, that equation. And this is finished. This is finished. In this whole process, we actually did not quite mention the function perspective, right? Yes, these are true. These are, what do you call it? These are if statements, right? These are if statements. All right. So about the other function perspective, right? It's about the other function perspective. If you look at the function perspective, we certainly can treat this as a function. Okay, we certainly, the function perspective. The function perspective, I'm going to put it as a note because these are typically not done. But as the way I always been doing it, I always want to give you the function perspective, right? The function perspective basically is saying, okay, the function we have is this piece. So we actually do have a function. Okay, so this is the function. This is a function. How does the graph look like? Graphing this function actually, it's not quite straightforward. So we have technology, so we use it. Right, we have the technology, so we're going to use it, right? You can see the curve show up in the domain. And if we make adjustment to the view, right? If we look adjustment to the view, and we get a picture. We get a picture. And this is the picture. Okay, this is the picture. This is the picture. And when the output equals to log base 5 or 20, right? So we're going to draw a horizontal line. We're going to draw this horizontal line. Okay, I'll make it red and a broken line. It touches the curve at a point. And we just found that point is 4, right? The input for that point is 4. The input is 4. And the output is this piece, okay? So now if we mark it, if we mark that point, okay, that point is 4 and log base 5 of 20. That is the point. So there is a function perspective, okay? That is the function perspective. And this curve, even though not all curves are the same, right? Not all the curves are equal, but it does show, but you can see all of these the points are pretty difficult to identify. For example, where it crosses x-axis. We know that it's less than 1, right? So it takes some energy to actually graph or sketch this graph properly. Even if you have technology to graph it, you still have to estimate the points. We are fortunate in this case that the solution is a 4, right? And so these are the cases that, you know, we're dealing with, okay? But yes, it does have a function perspective. It does have a function perspective, but we choose not to use function perspective to solve the question completely, but you certainly can use it as a reference. Once again, this reference tells us how many solutions is to be expected, right? Certainly in this case, we only have one solution. We only have one solution. And -5 is outside the domain. So we don't see that, right? We don't even see that curve going out to the other side. Okay, so this is the first example. Okay, so let's work on another example, right? So we still have this title, right? This time it's example number 2. Okay, this equation goes like this. We have a log base 5. Log base 5 again, x plus 1 minus log base 5 of x minus 1 equals to 1. Okay, we certainly have domain requirement here, right? So we're going to work on the domain. The domain has to satisfy that both parentheses must be guaranteed positive. So x plus 1 must be positive, right? And x minus 1 is going to be positive. And solving these two inequalities, we get x is greater than -1 and x is larger than 1. Okay, x is larger than 1. So I'm going to borrow this number 9. Okay, I'm going to borrow this number 9 and do it again. Of course, we're going to redraw these, right? So I'm going to redraw. Okay, so this is the number 9, larger than -1 and larger than 1. Okay, so here's the -1, right? Here's -1. So larger than -1, meaning that all of these are larger than -1. Larger than +1 are from here, right? So any place that's been marked twice, and that's will be the domain. And obviously the combination of these two is x larger than 1. Larger than 1. So when we are graphing the domain would be larger than 1, and there's going to be a circle, right, at that point, meaning that that point is not, 1 is not included. Okay, so that piece, that's the domain. That's the domain. Okay, so both conditions must be satisfied. Now, everything is going to be done in the domain. Okay. I'm going to save this piece for me for future use, right? For future use. So I'm going to delete all that. So we're going to just keep this blank thing for us to use in the future. So now we can start solving this, right? So everything is done in the domain, and we solve this equation, and quotient rule would apply. Okay, quotient rule would apply. So I'm going to bring our quotient rule, product rule, okay, to our side. Okay, so this is the product rule, quotient rule, and power rule. Okay, product rule, quotient rule, and power rule. So here we got log base 5, x plus 1 over x minus 1 equals to 1. Okay, and we can use definition. Okay, we can use definition, or you can use function perspective or whatever, right? I think using definition would be the most straightforward. Do we still remember the definition? Definition goes like this: log base b of omega equals to triangle if and only if, right? If and only if b raised to the power of triangle equals to omega, provided the base is larger than 0, not equals to 1. So here we have a base 5, right? And omega is this quotient, and triangle is 1. So we're going to have 5 raised to the power 1 equals to x plus 1 over x minus 1. And you can put this on the other side. Okay, you can put it this way too. Okay, which is more suitable to our custom. And then we're just solving for x, right? X is guaranteed to be larger than 1, so we don't have any worries about domain. And x minus 1 is not a 0 because x is larger than 1. At this point, we can multiply both sides by x minus 1, which is using principle number 4. Okay, so we multiply x minus 1 on both sides. Okay, on the right-hand side and left-hand side. Left-hand side is just x plus 1. Right-hand side is 5x minus 5. Put all the x together, so we're gonna have 4x, right? 4x, subtract x on both sides equals to 6, right? And in the end, x equals to 6 over 4. 6 over 4 reduced to 3 over 2. And then we're gonna go the domain check. Okay, is it in the domain? So the first thing we do is domain check. Well, x equals to 3/2 is in the domain indeed. Right, is in the domain. Secondly, just in the domain is not enough. So we have to go back to the original equation to work on the left and right, right? So on the left side, on the left-hand side, right? And we want to make sure it's equals to 1, right? The right-hand side equals to 1. So the right-hand side equals to 1, right? So we want to take a note of that. And plug in the numbers, right? We're going to plug in the numbers. When we plug in the numbers in 3/2, it's going to be in the place of x, right? And then we're going to simplify. And 3/2 plus 1, that's going to be 5/2, right? Because that's just 2 over 2. That's going to be 5/2, right? So this is going to be 5/2. 3/2 minus 1, that's going to be 2 over 2. And that's going to be 1/2, right? So that's going to be, wait, that's going to be 1/2. What did I do? Wait, how did I mess that up? Huh. Let me rewrite it. Sorry, I don't know what I did. Okay, so log base 5, and this is a 5/2, right? Minus log base 2/5. Oh, sorry, log base 5, 1/2. Okay, and then we're going to use the, we can use a quotient rule actually. Okay, so we get log base 5 of 5 minus log base 5 of 2 minus, right? We can get a quotient rule for that piece and be very careful. So that's going to be log base 5 of 1 minus log base 5 of 2. Log base 5 of 5, that's equals to 1, minus log base 5 of 2, we don't know, minus 1, minus log base 5, 1, this is going to be 0, right? That's going to be 0. And minus negative log base 2, 5, that's going to be a plus. And so these two make 0. And in the end, we got equals to what? 1. We got equals to 1. Okay, and that is the right-hand side. And that is the right-hand side, right? So now Now we have left equals to right when x equals to 3/2. Then you can say thus or therefore, right? X equals to 3/2 is a solution to the equation. And what is that equation? You always refer to the original equation. So this is the whole process of solving this equation here. Okay, so let me show you the whole thing. Does it show all? No. 100%. Let's see if that shows. Yep. Okay. So from the beginning, right? From the beginning, we determine domain, and then we go down the steps and finding the solution, and then check the solution. And this is the typical requirement of doing these kind of questions, okay? And you first determine the domain, and once the domain is determined, everything is done in the domain, okay? So that's the second example. Okay, so sometimes we get to use a product rule, quotient rule. Sometimes you get to use power rule to make a single logarithm. So now let's look at another one. This is actually number 7 in the homework. Okay, I call it example number 3. And of course, the same requirement, right? Determine domain and solve the equation. And this one actually is relatively short. Okay, determine the domain and solve for x, right? So we have all the tools next to us, product rule, quotient rule, and the equation here is like this, okay? Natural log, and we got x squared minus 1 equals to 2. Okay, first we're gonna determine the domain. The domain is going to take the whole thing that's being taken logarithm. This has to be positive. This has to be positive.